Hello Internet! Welcome to the Empirical Sword, where science plus gaming equals awesome. I am Lore Master DLC79, and today I want to talk about disintegration rays and beams and other disintegrating things. We see them on Star Trek and Doctor Who, and even fantasy role-playing games have disintegration spells. But I can't science magic, so let's ignore magic and stick with science fiction. So, I'm not going to say that these things are impossible. Instead, I'm going to ask a question. The question is, what would it take to make such a device actually work? Not that I have any intentions of actually using such a device. I'm not plotting world domination or anything. Anyway, in our pursuit of trying to figure out what we would have to do to make such a device, first we have to ask, what's going on? What causes a rifle-type thingy to make an entire human body disintegrate and scatter their atoms to the winds? Exactly what's going on. And unfortunately, science fiction doesn't really give us any answers to that question. It's delivering some sort of energy to a human target and poof. So we can make a lot of assumptions, and I'm probably going to do a video on each individual assumption. So for this video, I'm going to make the assumption that it's some type of laser beam, and here science fiction is already misleading us, because if we're shooting a laser rifle, we would not actually be able to see the beam, and in every single science fiction depiction of a disintegration beam, we can see the beam. So that wouldn't happen. Also, it most likely would not be visible light, because if we're using a laser to deliver energy to the human body, probably the easiest way to disintegrate a human body is to boil off all of their water, which means we would need to be using a wavelength of light that has a resonance with water. See, an electromagnetic wave traveling this way has electric oscillations going this way and magnetic oscillations going this way. And a water molecule is polarized. It has a partially negative end going one way and a partially positive end going another way. And when an electromagnetic wave passes through water, it causes water to rotate or flip around or something. And basically it absorbs that energy, the electromagnetic energy, and converts it into heat. So the wavelength or frequency of light that most likely would have a resonance with water is in the microwave to infrared range, which is why microwave ovens make things hot. It actually heats up the water and doesn't really cook anything. I mean you can cook things. I mean, you can use them to steam things, but there's not really any actual cooking. It's mostly just heating the water. So, microwaves are invisible. So again, we would not be able to see the beam, even if the beam is reflecting off the air, we would not be able to see it because microwaves are invisible. So we have a microwave laser that's heating up our target enough to boil off all of the water in the human body. So now that we have kind of an assumption of what's going on, let's head on over to the virtual whiteboard. So we have reduced this question down to simply boiling off all the water in the human body. Well, we can reduce it even further by simply considering boiling off water. But to know this, we need to know how much water is in the human body. And to do this, we need to know how much mass is in the human body. Most human bodies across the planet have a mass between 60 kilograms and 80 kilograms. So I'll just choose 75 kilograms. It's somewhere in the range. Now we need to know how much of this mass is actually composed of water. And this is roughly 65%. With a slight disclaimer here, but I'll use 65%, and we just plug this into a formula. 0.65 times 75 kilograms gives us 48.75 kilograms. This is the mass of water in the human body if we assume that that human body is 75 kilograms and 65% of that is made of water. And remember this number, we are going to be using that the entire slideshow. So now if we're talking about boiling water, we're talking about thermodynamics. And if we're talking thermodynamics, we are talking about this equation here. Delta Q equals mc delta T. Delta Q, of course, is our heat, which is not so much a thing as it is a measure of a change in internal state, an internal state that we can't measure, at least not with these variables. And of course mass is, M is mass, C is specific heat, and delta T is a change in temperature. So the specific heat of water is 4,186 joules per kilogram per Celsius degree, and no, I did not memorize that number, I looked it up. Our delta T is our change in temperature. Our starting temperature is 37 degrees Celsius, which is the core temperature of the human body, and our final temperature is the boiling point of water at one atmosphere of pressure, which is 100 degrees Celsius. That gives us a delta T of 63 degrees Celsius degrees. And of course, our mass of water is 48.75 kilograms. So we just plug these numbers into a formula, and we get 1.286 times 10 to the 7th joules. That is the amount of energy needed to bring water, this amount of water, from 37 degrees Celsius to the boiling point. But wait, we're only bringing water up to the boiling point. We haven't actually boiled anything away. So if we think about it like this, our delta Q formula is working like this. We're taking water from a starting point and bringing it to another state. In this case, that state is just at the boiling point of water. But when water boils, we're pumping energy into it, and the water is being converted into steam or some other kind of vapor, which is carrying that energy away, which in a sense prevents the liquid water from increasing in temperature even further. So we're pumping energy into the water and creating water vapor without increasing the temperature, which tells us that our delta Q formula does not work here, which means that we need another formula. Luckily, we do have another formula. Delta Q sub V equals mL sub V. M, of course, being mass, and L being latent heat, latent being a fancy science word for hidden, and sub V standing for vaporization, which is a fancy science word for boiling. So what we do is we take our delta Q sub V formula and plug in some values. The latent heat of vaporization for water is 2.26 times 10 to the 6th joules per kilogram, and no, I did not memorize this number either. I also looked it up. And of course, our mass of water is 48.75 kilograms. See, I didn't lie. We're using that the entire way through. So we plug these numbers into the formula and get 1.102 times 10 to the 8th joules, which is the amount of heat needed to boil off this much water, if that much water is already at the boiling point. So we basically do some simple addition here, and we find out that the total amount of energy needed to bring water from 37 degrees Celsius up to the boiling point and then boil all of it away is 1.231 times 10 to the 8th joules. What does that mean? To most people, that's just a number. That means nothing. Well, let's think of it like this. If we convert this into kilowatt hours, because this is energy, and kilowatt hours is a measurement of energy. So if we convert this into kilowatt hours and find out the cost of that amount of energy, if we were to draw it from Maine Electric, which in New York City that would be about 18 cents per kilowatt hour, if I'm correct. Might be higher, might be lower. It's definitely higher in Hawaii, but it's lower elsewhere. If we assume 18 cents per kilowatt hour, this comes out to be about $6.15 for the amount of energy needed to boil away all the water in the human body. So what's going on here? That's fairly affordable. I mean, why don't we have disintegration rays as household appliances to take care of trash or annoying neighbors? Perhaps something else is going on here. So perhaps what we're missing has something to do with the efficiency of energy transfer. See, if you remember, the human body is not entirely water. There's some not water stuff in there that is bathed in water, which means as we're pumping energy into water to heat it up in order to boil it off, some of that energy is going to be going into the not water stuff, which means that our 1.231 times 10 to the 8th joules is not going to be enough to heat everything so that we can boil off our water. So how much energy is needed? Well, I'm not entirely convinced that that's our only issue. See, I think we have issues here as well, where the laser beam meets our target. And yes, I do know that lasers don't actually look like lightning bolts, but the lightning bolt is a lot more exciting, don't you think? More to the point, I think that there's going to be some amount of reflection when the laser beam encounters our target based upon what our target is wearing. Is he wearing a white shirt? Is he wearing a black shirt? I mean, he's getting blown up, so he might be wearing a red shirt. I think we also have issues here, where the laser is traveling through whatever. Is it a vacuum? Is it air? Is it very, very humid air? Is it dusty air? Maybe it's the air of another planet that's mostly methane. But the thing that I want to focus on is right here. The laser beam, the laser device itself. Real lasers range from approximately 0.1% efficiency to about 85% efficiency. And this efficiency is determined by many different things. I mean, first of all, what kind of wavelength are we producing with the laser? Exactly how are we focusing the laser? Overall, it has to do with the amount of input energy into the laser device and the output energy via the beam. And it can be, how exactly are we measuring the input energy? Are we measuring the energy input into the lasing medium itself, or are we measuring how much energy the laser itself is drawing from an electrical outlet, which is likely also powering a cooling system and possibly some control settings and computerized stuff. What I'm going to do is I'm going to assume that the future has very efficient lasers. And I'm going to rearrange this formula so we can take our output energy, which I'm going to assume is 1.231 times 10 to the 8th joules, and divide it by our efficiency, which I'm going to assume in the future is 90%. And we're going to get an input energy of 1.368 times 10 to the 8th joules. This is how much energy we need to pump into a laser device that is 90% efficient in order to get this output. So exactly what is this telling us? Well, it's telling us that some of this energy is wasted, and I'm using air quotes here because it's not actually wasted, it's converted into heat. Specifically this much heat, which is simply our input minus our output. And if we're talking about heat, we're talking about this equation here. That's right, delta Q is equal to mc delta T, which I'm going to rearrange in order to get our delta T from an M and a C. Which M and which C? Well, again, I'm going to have to make some assumptions here. I'm going to assume that our laser rifle is approximately 5 kilograms. And I'm going to assume that the specific heat of the casing of our laser is 8,372 joules per kilogram per Celsius degree. And I should point out that this is twice the specific heat of water. And water actually has a very high specific heat. Most things that have a higher specific heat than water are actually gases, not solids. So again, I'm giving the future a huge benefit of the doubt, and assuming that in the future we have some space-age polymers that have a very high heat absorbance capacity. But notice that even with these numbers, giving the future the benefit of the doubt, we still get a delta T of 327 Celsius degrees. And if we assume that our rifle starts out at room temperature, which is 20 degrees Celsius, that gives us a final temperature of 347 degrees Celsius. The boiling point of water is 100 degrees Celsius, so this is pretty hot. But keep in mind that I don't think that all of this wasted energy, again, air quotes, is going into the casing, at least not immediately. Most likely it's going to be going into the lasing medium itself, and is possibly going to raise the temperature of the lasing medium high enough to melt or vaporize. This is why lasers need cooling systems. And this cooling system is of course going to be consuming its own energy, and it's going to have its own waste, and here we're just complicating things. The point is that the cooling system is going to have to take this waste, this 1.37 times 10 to the 7th joules, remove it from the lasing medium fast enough to keep the lasing medium from destroying itself, and then put it somewhere, possibly in the casing of our laser rifle. which will still raise it up to almost 350 degrees Celsius, which is pretty hot. Now, I want to take this opportunity to also consider another issue. What would it be like to be in the same room if this happens? And we're going to talk about what happens to water when it boils off instantly, if that can even happen. First of all, we need to know the density of water, which is an easy number to look up. It's 1 times 10 to the third kilograms per cubic meter, and the density of steam is 0.63 kilograms per cubic meter. And of course, the mass of water is our 48.75 kilograms that we are using the entire way through. Don't worry, we're almost done with the slideshow. And of course, this is the same as our mass of steam. And of course, we can take the density of water and the density of steam and the masses and calculate volumes. Our volume of water is almost 5 times 10 to the negative 2 cubic meters, and the volume of steam is approximately 77 cubic meters. And if we assume that these are spherical, which is probably the case for our steam, but probably not the case for the water, but let's make an assumption. If we assume that our water starts out as a sphere, it's approximately 0.2 meters in radius, and the radius of our steam bubble is approximately 2.6 meters. So what exactly does this tell us? Well, this just tells us the change in volume. If we assume that this change in volume occurs in about 30 milliseconds, which is about 1/30th of a second, that means that our steam bubble is expanding at 80 meters per second, which is about 180 miles per hour. That's a steam bubble that's expanding outward at about 180 miles per hour. So we have laser devices that can vaporize themselves if they're not cooled, and if they are cooled, they make the casing so hot that you don't want to touch it. And if we can deliver all that energy into our target, it creates a steam bubble that expands very, very fast enough that you probably don't want to be in the same room with it. This is probably why we don't have these things as household appliances for waste disposal purposes or taking care of annoying neighbors. So the conclusions that we can draw so far are that if we assume that we're using a microwave laser to boil off all the water in the human body, thus facilitating a disintegration-like effect, even if we assume that this device is extremely efficient, we wind up with enough wasted energy that one of two things is going to happen. One, the lasing medium itself is going to heat up to a catastrophic temperature and destroy itself. Or two, we have to use a cooling system to remove that heat before the lasing medium can destroy itself and then do something with it. And the next logical step is to deposit that into the casing of the weapon, which unfortunately will make the weapon so hot that nobody would want to touch it, which kind of makes it a very impractical weapon, at least in the small scale. Furthermore, if we actually could boil off all the water in the human body instantly, which I don't think is possible, but if we could, the bubble of steam generated would be expanding at roughly 180 miles per hour. If wind is sustained at 180 miles per hour for at least 10 minutes, this is called hurricane force wind. Now, this would, of course, just be a gust, but still, I would not want to be in the same room with that, and I don't think many people would. So this is yet another reason why these things probably aren't very practical in the small scale. Now, yes, laser devices like this are being developed in the large scale, not for killing humans, but for destroying missiles. But let's go back to the point where I keep saying that I don't think it's possible to boil off all the water in the human body instantly, at least not with this method. Here's why. Let's imagine that you have a microwave laser and you hit me square in the chest with it. What's going to happen? Well, if we assume that my clothing is transparent to microwaves, and that the first thing that's absorbent to microwaves that the beam encounters is my flesh, what's going to happen? What's going to happen is all of the water right here in my chest is going to absorb hopefully all of the energy. Possibly a lot's going to be, reflected away or transmitted through, so it's not going to be a 100% absorption. But if we assume that what is absorbed is enough to boil off all the water in the human body, what's going to happen to it is it's just being absorbed here. And unfortunately, because the human body is made of cells that encapsulate water, the flesh is not exactly a good thermal conductor. So all of that energy, and thus all of the heat, is going to be trapped here. And if it's enough energy to boil off all the water in the human body, then it's going to be more than enough energy to boil off the water here in my chest. So when that happens, it's going to boil off explosively and away from me, thus carrying all of that energy away from me. Now, yes, the wound created would be very, very painful, if not lethal, but it's not total body disintegration. To boil off all the water in the human body, we would most likely have to expose the human body to an extremely hot environment, in which every surface on the human body is absorbing heat, and there's enough of a temperature gradient between the hot environment and the human body that the relative low thermal conduction of human flesh is negligible. So this would probably be like the inside of a volcano or the inside of a star. So yeah, I really don't think an actual beam could do that. Sorry, science fiction. What am I trying to say here? Think faster! Think faster! Think faster! Think faster! Think faster! If you like this video, then why not hit that like button? In fact, even if you didn't like this video, why not hit the like button anyway? Just to be nice, you can call it your good deed for the day. But if you really did like this video and you want to see more like it, then why not hit the subscribe button? Then my videos will just show up in your subscription feed. And you know what? If you have any kind of feedback at all, leave a comment. If you thought I did something wrong, or you've got something wrong and you want to let me know in a constructive, positive manner, then leave a comment. If you thought I did something really right and you want to congratulate me, leave a comment. If you have suggestions for future content, leave a comment. In fact, if you just have a simple question like what I had for breakfast, leave a comment. I can't promise that I'll answer all of them, but I will definitely try to read all of them. So until the next video, goodbye.